Hello. In this lecture, we study about planar curves which arise from a functional equation. So those types of curves are called level curves. So let us begin. Okay, so what are my level curves? So level curves are those curves arising from a equation of the form fxy equals to 0. So where this f is a function from u to r is a smooth function defined on an open set u of r2. So that is, so what is the meaning of smooth function? So that is, so all the partial derivatives, so all the kth order partial derivatives of x of f exist, and they are continuous. So for all k greater than equals to 1. So this is the meaning of smooth function. So suppose we have a curve arising from a function from this type of functional equation. So we call that to be a level curve. So for example, so let us take, so let f r2 to r is defined as follows. Let f r2 to r be defined as fxy equal to x square plus y square minus 1. And if I take this equation fxy equals to 0, so this means that so x square plus y square equals to 1. So this represents a unit circle. Okay. So note that, so not always this fxy equals to 0 will represent a curve. So for example, so instead of taking here x square plus y square minus 1 equal to 0, so we can take, so let gxy equal to x square plus y square. So if I take gxy equals to 0, so this means that x square plus y square is equal to 0. So this means that x and y both are my 0. Okay, so it represents a single point. Okay. All right. So Now again, let me come back to this example. X square plus y square equals to 1. So fxy is equal to your x square plus y square minus 1. So this fxy equals to 0. So it represents this unit circle in R2. Okay. So this is my unit circle in R2. Okay. So now if I take any point uh, on this unit circle, so let us take this point. So this, let us call this point to be my x naught, y naught. So here, so if I take this point here, x naught and y naught both are not equal to 0. And observe here that, so if I take a small portion of this, so this small r, it is a, so here you can, so write like this. So any point here, you can write x comma root over 1 minus x square. So, so this small arc, so it is a graph of a function. Yeah. So here, so if I take this phi of x to be your root over 1 minus x square, so here, so this portion is graph of phi x. Okay. So now if I take this point, if I take this point, so this is my 1 comma 0. Okay. And now if I take, let us take this arc. Okay. So here you can see that, so this you cannot write as x comma some psi x. So it is not a graph of a function over the x axis. Okay. But here, so you can note that if I take the y axis, so this red arc here, it is graph over this part of this y axis. Okay. 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 So here note that so if I compute the partial derivatives, so del f del x, so this is equal to twice x, and del f del y, it is equal to twice of y. And what is my partial derivative at the point 1 comma 0? So this is equal to your 2. And what is the partial derivative at of y of f with respect to y at 1 comma 0? So this is equal to your 0. Okay. So this del f del y, it vanishes at the point 1 comma 0. Okay. So because del f del x at the point 1 comma 0 is not equal to 0, so I can write this x as a function of y. Okay. So here, so this, so for this x will be equal to some psi y, and uh, and this, so what we can write, so this psi y square plus y square, so this will be equal to your 1. Okay. So now let me do a general case. So this is one example. So the general case is called implicit function theorem. So I'll be not proving the theorem, only I state the theorem. So implicit function theorem. Okay, so what does it state? So let us take an open set in R2. So let U be an open set in R2 and F be a smooth function defined on U. Okay. So now assume that, so assume, so del f del x and del f del y are not both 0 on this open set U. Okay. Okay. So now, so if fx f x naught y naught is equal to 0 for some x naught y naught in U. Okay. So then so the following holds. So then the okay. So now you take the partial derivative of f with respect to x at the point x naught y naught. So if so this is not equal to 0, okay, so then so this in a neighborhood of x naught you can write x as a function of y. So then there exists an open interval I containing x naught in R and an function psi defined on this I such that so this f of uh, psi y comma y is equal to your 0. Yeah. So here, so this open interval I, it contains y naught, not x naught. So such that this f of psi y comma y is equal to your 0. Okay. So such that this happens, and also x naught is equal to your psi of y naught. Okay. And next, so if del f del y at the point x naught y naught is not equal to 0, so then there exists an open interval J containing x naught in R and an function phi from J to R such that uh, f of x comma phi x is equal to 0 and phi of x naught is equal to y naught. Okay. All right. So I have assumed this function f to be your smooth. So in fact, the function psi and phi you will get, so that will be also a smooth function. So this in fact, so this psi and phi, so these are my smooth functions. Okay. So now what is the application of this? Okay. So let us take a function. So let f R2 to R be a smooth function. So such that so the partial derivatives del f del x and del f del y are not both 0. Okay. So this means that at least one of them will be not equal to 0. Okay. So suppose so del f del y at some point x naught y naught is not equal to 0. Okay. So now let us take this plane and so suppose this is my curve. It is something like this. So this is my yeah. So suppose fxy equals to 0 represents this curve, and this point, so let us take it to be my x naught y naught. Okay. So here, so the partial derivative, so this del f del y, it is not equal to 0. Okay. All right. So if I now take this point, will be your x naught comma 0 on the x-axis. So by implicit function theorem, so what you can tell, so you can have a small open neighborhood of this point x naught comma 0, and you take the corresponding portion here. So this small portion, so this will be a graph of a function. Okay. So this is so any point here, so you can write as x comma phi x. Okay. So this interval is my j. Okay, so x is varying in j, and this y naught is equal to your phi x naught. Okay. Okay. So now once you have this thing, so with the help of this, you can determine the curvature of a level curve. Okay. So suppose you have this thing here. So what will be the curvature? So curvature at x naught, y naught. So again, let us assume. So suppose, so this del f del y is not equal to 0 at the point x naught, y naught. Okay. So if you assume this thing, and now if I take this curve, so alpha t equal to t comma phi t. So t is varying in this interval j, which contains the point your x naught. Okay. So then f of t comma phi t, so this will be equal to your 0. So this alpha, it is a map from j to your R2. Okay. So now you can compute the curvature of alpha. Okay. So curvature of the level curve fxy equals to 0 at x naught, y naught is equal to curvature of alpha at alpha t naught. Okay, so what is your alpha t naught? So alpha t naught is the point x naught comma y naught. Okay, so what will be the curvature here? Yeah, so the curvature here, it will be equal to mod of this phi double prime t naught divided by 1 plus phi prime t naught square to the power 3 by 2. Okay. Yeah. So in this way, we can compute the curvature of a level curve. Okay. So I'll stop here. I'll continue in the next class.